At the beginning, I would like to thank Dr. Rajneesh for inviting me for this meeting and the organizers for the excellent arrangements. It is flawless for everything. Thank you very much. So, I'm I'm basically a computational chemist working on different computational models to work in the domain of chemical and biological sciences. So, here I will walk through the key challenges that we face in selecting the computation models for molecular or materials properties. So, the method we choose depend upon the size and the complexity of the problem. So, we need to be very careful in selecting these methods because it is a computer, right? It is a method, computational method. So, whatever we give, it will give some number. So, we need to be careful and we have to have some kind of fundamental knowledge about these methods. So, I am coming as Dr. Nandini mentioned, I am coming from one of the 37 CSIR labs. It is Indian Institute of Chemical Technology located at Hyderabad. Basically, it is a chemical sciences institute and its strength is in synthesis of organic molecules like different active pharmaceutical ingredients and small molecules and so on. So, we have a wide expertise in several areas at IICT and we are entering into 80th year of our foundation. And our mission is to create outstanding knowledge in both chemistry and biological sciences. So, as I do not think there are many computational expertise here, right, in the audience, though there are very few. So, many people think that a wet lab is very tough and you pass through several challenges in making the synthesis and all. And they may think that working on computer is a kind of silicon work and we have always AC rooms, working very leisurely, luxurious bench and everything. But it is not like that for every time, you know. So, it is always see that there are some issues popping out at every stage and we need to work align with experimental people and try to understand why the numbers the way it comes from each method. So, it is as tough as any other wet lab. So, coming to the some fundamentals before I can speak more about the essence of this conference, that is CO2 capture and sustainability. Just a few slides for the sake of students. It is a jargon of nomenclature, right? You have often use the overlapping terms molecular modeling, computational chemistry, theoretical chemistry, quantum chemistry and so on. But though the jargon is varies, the goal remains the same. So, goal is to predict the materials or properties of a given system. So, India is blessed fortunately with several eminent theoreticians who have developed several methods. To say a few, Debashish Mukherjee from ISES Kolkata and Professor Gadre from Pune and Jemmis and Kalidas Sen, Mahapatra and Durga Prasad and Satyamurthy from ISER and Subbu sir from CLRI. And these are the very prominent theoreticians who actually work on the method development. They are called theoreticians and they have established a very core of computational group in India. By any chance, if any of research community, if they are collaborated with any computational chemist, invariably they have a lineage with one of these people. So, that is the beauty of our expertise in India. So, here I want to compare the four paradigms of our science. So, you can see that empirical, theoretical, computational and data driven approach, each paradigm has its own strength and limitation, because you can see that computational methods help study to complex systems, but it has its own set of challenges. For example, empirical methods need experimental validation, and a data driven method depends upon the accuracy of the method, and also it depends upon the quality of the data set you are using. So, these are the four paradigms that generally they put forward for any computational methodologies that have been developed till now. So, there is also called fifth paradigm, that is industry 5.0, and if chairperson allows me, I can talk one or two lines on quantum computing, which is, I think it is much essential for current generation students to put forward to start their efforts in understanding quantum computing. Okay, I'll just see whether it is possible or not. So, yeah, yeah. Mm. So, what are the major problems in computational methods is it involves lot of approximation. It predicts properties at 0 Kelvin. However, to interpret real world properties like temperature and reactivity, you need some validation either through experiment or any other mode. So, but the advantage is, yes, this slide deliberates experiments and takes weeks and months, years to come up with some prototype or any other output, whereas computations are very good to do to begin with for identifying the lead candidate. So, each model from empirical to ab initio comes with some approximations. So, choosing the level of the theory depends upon the nature and the size of your problem. So, as I said, the computation helps in scanning the whole range of periodic table and so many combinations that are available, and screening the molecules, for example CO2 capture. There are so many solvents, adsorbent available, right. So, using these protocols or methods available, you can screen hundreds, thousands of these molecules effortlessly. So, as we go from large to small atoms to large assemblies, there are several other variables that comes into picture. So, in the data driven approach, so as this meme tells you that okay, the initial enthusiasm to work on the machine learning project, but it depends upon the quality of the data. Like if you so for example, many AI many ML projects like in insurance, in banking, it all depends on the population, which is the data is really accessible, and you have a access to valuable and real data. So, it is very easy to get very quality data there in in those sectors. But coming to science, these experiments are done at different temperatures, different reaction conditions, and they report at different journals, and they do not report the negative results, right. So, they want to please referee and editor. So, they do not hide, but they do not publish the negative results. But to get a real very good model, you need also the negative data. So, it all there are several errors that comes when you try to do the data driven models because of these flaws. So here the just a second. Yeah, so in all these cases, as I mentioned before, so whatever you ask the computer, it gives some number. Is it a garbage in, garbage out? Absolutely not, right? So regardless of the sophistication of tools that are available to predict the properties, there are some challenges or limitations to get the misleading results. So it all depends upon the choice of the method and the size of the problem. So, what kind of properties you are looking to have these computational studies, right? So, you want to do energy of a given material, for example, catalyst material or any drug protein enzyme interaction or any organic reaction mechanism you want to, because it is very difficult in organic reaction to locate, identify the transition state, right? So, how it is easy, it is not very much easy, but you can do computationally to predict the structure of the transition state, and you can predict several energetics, and you can predict at several parameters that are useful to develop a prototype. So, it always depends how you interpret these numbers with the with experimental results or validation. So, then the critical point is to choose the model. How do you choose? Like yesterday we have seen Dr. Varghese presentation, how he has done the microkinetic modeling for his catalytic reaction, right? So, he has used some models, but computationally how close is to the realistic experimental condition. Like for example, if you take, sorry, it went to, so if you take a cluster of some metal, transition metal, for example nickel cluster, which is there on a support for alumina or calcium or anything. So, at the realistic experimental conditions, many catalytic reaction takes place at 1000 degrees, 800 degrees and so on, right. So, at those conditions, these clusters will not remain what we do for computational models. There are several variations. How do we take into account in doing the computational studies? That is very important for the for predicting the properties. So, there is always trade off between accuracy and the computational time. So, as we see here, so it depends upon the size of the molecule, where you can start with dealing with a single atom based computational models to single atom to molecule and to the supramolecules. So, in all these cases, most of these molecules and supramolecules, it is the interatomic potential which is very important. What does it mean? Because for these supramolecules, they are governed by some non-covalent interactions. These non-covalent interactions are very different types, like you have electrostatic, van der Waals and hydrogen bonding interaction. How good is your method is able to capture these kind of non-bonded interaction to predict accurately with the experimental number? That is the critical point to note. Okay. So, what method we have to choose in understanding the experimental observation. So, as you see that classical mechanics is guided by Newton laws of motion, which is majorly governed in molecular mechanics and molecular dynamics, always used for big complex systems like biological systems like protein, enzyme or drug interaction, and whereas the quantum mechanics is governed by Schrodinger equation. All of you know the Schrodinger equation, right? So, this is governed by Schrodinger equation, which after taking into several approximations, you all know the Oppenheimer. You have seen Netflix Oppenheimer series, very good, right? You have understood something from it, from his a little bit, yes, fine. So, what does Oppenheimer tells, right? He said nucleus electron approximation, right? So there are several approximation in this calculation to accurately predict the numbers for the experimental validation. So, but as this is my I am really motivated with the you have to read lot of books by Richard Feynman. You know, Richard Feynman and Dr. Einstein, they have predicted the quantum computing in those days, way far back in 1930s. Okay, so he has the famous quote from his book is, there is plenty of room at the bottom. So, and as I said, the choice of this computational model depends upon the size of your system. Like if you want to do only one electron system, what is it? It is hydrogen, right? So, if you want to do, you can do highly accurate quantum mechanical methods which is within 1 angstrom of its size. So, if you slowly increase the size of this of your problem, the method also varies, and it depends upon the and it also the accuracy and the time taken for the calculation also will change. So, for example, our group has been studied on several perovskite structures. Have you heard of perovskite? Perovskite structures. It is the highly stable structure that has been used, that has been under development to replace the silica based solar panels. Okay. So, these perovskites are highly stable, and to study such kind of model system, we are using molecular mechanics kind of method. And also for molecular dynamics, you see this is the titanium dioxide, which is linked to several amino acid moieties to see how it can capture the CO2. So, this is the time dependent study which comes under mesoscale modeling. So, which will give you the time dependent. So, this is one kind of spectrum where you get the contribution from each orbital. So, like that, the change you have to choose the appropriate model depending upon the size and the complexity of the system. This is very important for students to understand, to choose the methodology for their work, because invariably at some point of your research career, you need to take support from computations for at some time or other. So, it is important for you to see, at least you do not need to in depth of knowledge, but at least you know which method the collaborator is using. Is it a suitable or appropriate method for your problem. So, you can have either for a structure based study, or you can have a dynamics of a kind of study, like a protein. It is constantly varies, right? It is tried to it is tried to change its shape and 3-dimensional configuration, right? So, such kind of, if you want to study the protein ligand interaction, you cannot have only one structure of protein. It has to have a time dependent structures you have to take into consideration. So, for such kind of studies, you need to choose the dynamic studies, whereas for structure based studies you need to take the static, that is the structure based study. So, for this you have ab initio based molecular orbital methods, Hartree-Fock, which is very popular, and all of you know about the density functional theory, whereas we use lot of molecular dynamics and grand canonical Monte Carlo simulation. Coming back to the core of this theme, what we do in our group at IICT for CO2 capture and for conversion of CO2 into several feedstock. So, apart from our basic academic type of research for using different computational tools for drug discovery or understanding materials property, we do a data driven study for identification of lead materials, mainly for catalytic material for conversion of for the, especially for 2 case studies that I will briefly give you the details. So this is the workflow. One is, so I'll just give you very briefly 2 case studies where we are using this computational method. One is reforming of methane or conversion of CO2 to different feedstock, that is one study. Another study is screening several small molecules, either amines or solvent, for capture of CO2, either from point resources like thermal or power plants or from direct air capture. So what we do is, for reforming of studies, reforming of methane, we start with the materials for which is representative of a catalytic model, like nickel cluster sitting on the alumina or iron, or any catalytic material doped with different transition metals sitting, because for this reaction they use calcium oxide as the sorbent. So we try to combine in our computational model both the catalyst and the sorbent in a single particle, and try to develop the models, optimize the model, and try to predict the properties for these conversions. Similarly, we screen these amines. Yesterday we had a good talk for Sanjay, Dr. Sanjay Singh, where he has used solvents for direct air capture, and also for from Ramesh from IIT Chennai, where he has used different solvents for CO2 capture. So similarly, we screen several amine solvents, how good they are in capturing the CO2. In I cannot say capture because it's a broad term. So at a computational level, I can say how well it reacts with the carbon dioxide, forming the carbamic acid or any other properties, any other products. So for this we work in line with experimental colleagues, where whatever lead compositions we give them, they try to synthesize and try to work for their CO2 reactions. So these are the, for the catalytic materials properties, these are the summary of some of the properties what we usually try to predict. So bond length, bond angles, and other electronic and optical properties. So this is the overview of the entire workflow what we do for the reforming reactions. So we just initially we try to take the literature review to see what are the, because reforming of methane or any other gas is not a very new, it is a decade old problem. So there are several literature reports available online, but as I said in the beginning, it is very challenging in converting that data into a realistic model. So we have almost spent 2 years 6 months of time in converting the reported literature into a meaningful data set for our AI model development. Likewise, we have identified a few compositions and then did DFT studies to understand, to predict some of the properties, it is called key performance parameters, and gave our compositions to the experimental colleagues, where they have developed this nickel calcium oxide based materials, and then they have tested in this reactor for methane reforming. So that is one study. Another study, as I said, we have screened the several solvents, amines, for the CO2 capture. So what we are interested is, when the gas is purged into this amine solution, when it reacts with this amine, it will form a product which is very different from the beginning. That is, it forms from liquid to solid phase. So, once the solid phase is formed, it is easy to separate out, and then it is unlike the traditional method, the regeneration energy will be much less compared to the conventional method. In that way, we can save lot of operating cost. So, this is the focus of our study to screen the amines, and that we have used, as I mentioned, we have used a lot of literature data to screen reported amines and solvent. And also I am again emphasizing that the choice of method, and there are several solvent models that are available to select for your problem. Okay, that model is also very important, whether it can be able to capture all the interactions. So, this is one slide giving the summary of workflow, what we have done to screen the amine molecules and how we have synthesized, and then synthesized and then tested, validated. As you can see that once it reacts this amine in a given solvent, if it reacts with the carbon dioxide, it forms a solid form. And then we have developed, because since it is a CSR lab, right? So, they will not appreciate until you take to the pilot scale. So, we have developed the process for this with the help of chemical engineers, and the patent is also is also granted actually. So, as you see here, this is our composition of solvents, where it is energy required is much less than the reported amines. So, you cannot trust me, we have tested 154 compositions of these amine in different solvents before arriving at these 12 successful solvents, where it has shown very good liquid to solid conversion. So, we have taken, I just want, since it is a sustainable conference, we also have taken into consideration the choice of solvent. It has to be environmentally benign, and it is easy to synthesize. There is no again CO2 emissions in the process. And though we have not done LC analysis, but we see that there is much less environmental hazards in creating this method. So, this is a short video where CO2 reaction with the given amine in a solvent give rise to a product which solidifies, and very quickly within 1, 2, 3, 4, 5 minutes you can get the solid, and which can easily be separated. So, only the precipitate you can regenerate for the next cycle. So, in this way you can save lot of energy. So, think about the contribution of computational support in doing this experiment at every stage. So, that we have collaborated with our experimental group. These are the list of some softwares, because we are not a group which develop the methods, but we instead we use the available open source and also the some of commercial software to predict the properties. Vienna atomistic simulation package is very useful software developed at Austria, and you all know the Gaussian, Quantum Espresso and other software, and then we use Python for our AI ML model development. This is the entire team that we are working together for this important problem for CO2 capture and its conversion. So, I thank all my team members and also the funding agencies which is generously funded all our projects, including mission innovation, in-house CSR mission projects, and it is SERB when we started, now it is ANRF, and obviously the Board of Research and Nuclear Sciences, that is BRNS. So, I thank you for your attention.